Dario Rosa. Dario finished his PhD in, I'm sorry, in
2014.
Yeah, in Milano. Yeah. In Milano, okay. And then he spent 9 years in Korea, in different institutions. Incredible. At that time, he was also awarded the prize of Researcher of the Year in 2020. He was also awarded many others grants. And finally, he did the right move when he came here to IFT, right? And so he's here since the beginning of the year. And most importantly, he's the new Colloquium organizer.
Yeah.
Okay? So welcome and good luck.
Yeah.
Right, right. A big responsibility for the kind of, right? Exactly. Yeah, exactly, exactly. Forget the transparencies and go to the blackboard. Anyway. And so thank you very much for accepting our invitation. Today he's going to talk on the challenge of quantum many-body systems, or why computational power isn't enough.
Yeah.
Okay, thank you very much.
Thanks a lot. Yeah. Okay, so yeah, as anticipated by the title, the idea of today is to discuss a little bit what are, or what is, because essentially it's just one, but very hard, what is the main challenge when we deal with quantum many-body systems, and as the title say, why just using brute force computational power isn't enough in that case. So let's start a little bit. By the way, interrupt anytime, such that we can entertain a bit more. So let's start a little bit by recalling what I mean by computational power and a little bit of historical context. So what I mean is that, let's say, in the last, roughly speaking, 20 years, we had an incredible speed up in, let's say, our computers. For example, I remember I was a kid around 2000. If you were buying a PC, you were having, so let's say a PC, you were having a RAM. People in the audience don't know because they are too young, but I was a kid, and you had a RAM of 128 megabyte. 128 megabyte. And the hard disk was around 15 gigabyte. Now you cannot even install Linux on that. Then we make a span, and now we buy a laptop, let's say a good laptop, but still a laptop. And you have, let's say, 16 gigabyte of RAM. And you have an hard disk that is like 500 or even 1 terabyte or even more of memory. So in 20 years, we got this incredible speed up. And this already gave some, let's say... That's not the speed, right? No. Yeah, it's even more. It's even better. It's even better. But let's say, I mean, you will see in a moment why I focus so much on the RAM. Because when you deal with quantum many-body systems, of course, the speed is super important, but sometimes the RAM is even more, because sometimes you have to sacrifice speed to increase, let's say, to optimize the memory consumption. So that's why I focus on the RAM. But in any case, the speed is also even more. And this already gave some very important, let's say, science and technology outcome. So let's review, since this is a colloquium, some of them. So one of them that, in my opinion, is astonishing is in medicine, and in particular in, let's say, cancer treatment. So while preparing this colloquium, I read a little bit, and I discovered that in 1985, an Italian, Renato Dulbecco, I think he got the Nobel Prize. I'm not sure. I think, yes. Okay. He came out with this idea. He said that essentially sequential genomic will be, let's say, key in order to find new cancer treatments. And okay, I cannot enter in his mind, but I think the idea was more or less the following. In the standard chemo, that is still used, but let's say it is now the standard. So in the standard, I mean, at the time was also, but was the only option. So the idea is that in the standard chemo, I use this approach because I think we will be something similar later in quantum many-body systems. Of course, I'm not saying that cancer has anything to do with quantum. I'm just saying that, let's say, it is a many-body problem, but it's not quantum, fortunately. So in the standard chemo, essentially what we do is to recognize a very, but very trivial pattern. Essentially, we recognize that cancer cells are very fast in, how can I say, in splitting, let's say. So they recognize that a common feature of essentially all the cancer cells is that they split very rapidly. And so what we do, well, we simply create poisons that recognize, and let's say that they target mostly very rapidly splitting cells, with the hope that this poison will affect mostly the cancer cells. This is the reason why chemo also, let's say, destroy our blood cells, destroy our sometimes our hair and so on, because essentially the only, let's say, criterion to decide who this poison should attack is that. Now let's do again another long time step, and we go to 1998, so essentially at the beginning of 2000. And in this moment appeared the very... okay, and I think Dulbecco idea was the idea that if we do sequential genomic, so if we study more, we will develop more patterns, we will see more patterns, and we can do more targeted therapies. Let's say we recognize a better pattern, more, let's say, specialized than just this trivial pattern, and maybe we can do something better. This started to happen in 1998, in which we had the very first treatment, let's say targeted treatment. As far as I understand, at the time, the very first targeted treatment was for a form of breast cancer, in which they recognized that this form of breast cancer has a particular, I don't know, chemical situation for which you can do a specific treatment. Nowadays, I will say that, so 2024, this kind of, let's say, targeted treatments are becoming, let's say, not yet, but they are becoming standard. So we see that, and essentially this is really, let's say, in some sense, driven by a sort of computational power. We increased our ability to compute, if you want, to study the genome at very precise. We could find patterns that are, let's say, common to many cancer cells, and now we can do, in many cases, this very targeted therapy. When we develop a cancer, sometimes doctors can tell us how much a certain therapy can work or cannot, depending on the very specific features. So this is, I think, an astonishing result of the computational power. Now, let's do other couple of examples. Both of them are in AI. So in AI, for example, something that again, I was a kid and I remember this case. It was, I think, 1997. IBM produced, let's say, built Deep Blue. Now, nobody probably remember what it was, and again, you were too young for that, but it was the very first supercomputer targeted to just play chess, and it was the very first time that Deep Blue was able to defeat Kasparov. Again, let's do now. Now we go to 2020, and nowadays, your phone beats Kasparov without any problem. So again, there is nothing magic about that. Programmers have not become any better in playing chess, in doing programming. It's just computational power, essentially. Finally, and this is really, let's say, funny in some sense, again AI, the second one. Let's start with the 1970s, 70-ish, let's say, I don't remember exactly, but during this time, more or less. There was an important, let's say, computer scientist called Minsky, who made a prediction. 8 years, computers will chat with us. It was definitely an optimistic person. But now, in 2022, we started to have ChatGPT that essentially is doing what Minsky was, let's say, assuming to be true in 8 years. He was definitely an optimistic. Even more optimistic because, unfortunately, 2016, he passed away. So he couldn't see the realization somehow of his prediction. But nevertheless, he was not so far to be, let's say, from the truth. So I think this, and again, this is, if you want the theory, as far as, again, I'm not an expert, but as far as I understand, the theory in order to build the ChatGPT was well known at the time of Minsky. This theory of, let's say, neural networks and so on is nothing new, nothing recent, nothing. It was just that the computational power was not enough. And contrary to Minsky's prediction, it took much more than that. Now, so let's see, now let's go to, let's say, the real content of the talk. Let's see what we have been able to do in quantum many-body physics. So, okay, quantum many-body physics is, let's say, a large bit. So let's say what about quantum many-body, let's say, physics. So quantum many-body physics is a huge, let's say, beast, and I don't want to generalize too much, also because maybe people then will complain about what I say. So let's try to be a little bit more specific, and let's focus on a particular aspect that is one that I like more, which is the so-called many-body localization. Many-body localization. Let's introduce a little bit what it is, and then we will see what happens. So let's assume that we have a system of n qubits, which for sure everybody knows what they are, but just to remind, these are just, let's say, two-level quantum systems. So let's say we have the state 0 and the state 1, each of them. Okay? And so let's say that, for example, we have, let's say, a chain including these n qubits, and each of them can be, let's say, in state up, that, let's say, is 1, state down, which is 0, and so on and so forth. And now, let's say that we focus on a particular Hamiltonian. So let's say that the dynamics of these n qubits is controlled by an Hamiltonian that I write here. And then we comment a little bit. So let's say that this is the summation for I going from 1 to n, let's say -1, of sigma I plus 1, plus, and this is in a sense the interesting part, hi sigma I z. Okay, let's comment a little bit. So these are simply the Pauli matrices acting on the qubit I. So let's say these are simply, let's say, sigma I x, sigma I y, and sigma I z. And here we have a first term that is, let's say, interacting. You have also the interacting term here. Let's say the interesting part is here that make the model disordered. Okay? Disordered because these variables, hi, which can be thought as magnetic field because essentially, let's say, they tend to polarize our system according to the Pauli matrix along the z direction. These hi are, let's say, random variable extracted between -w and, let's say, w, where this is the disorder strength. Okay, and now, let's say, the main question in many-body localization, I will not spend so much time on why this question is interesting. If you are interested in knowing why it's interesting, you should register to my course.
Dario, just a question. This hi reflects what physical aspect of the system?
Hi, well, you can think that this is a system of n spin that interact, let's say, nearest neighbor via the first term, and the second term is a random magnetic field. Random. Yes, so in each point you have a random magnetic field that can be between -w and w, where w it's the strength of this disorder. Okay. Okay, so let's say the idea, one of the, let's say, the question that people in this community have addressed is, suppose that I create an initial state that I call psi 0, that, for example, is the state in which I put the spin 1 up and 1 down, let's say, in this way. So I put the n spin 1 up, 1 down, 1 up, 1 down, and so on. Then I do time evolution. We know that the Hamiltonian creates the time evolution, so I do time evolution, and I get psi of t equal to e to the minus I h t psi of 0. And I ask what is called the return probability. So the probability that at a certain time t, my state, my evolved state, is again in the initial state. So I ask psi t psi 0 modulo square. And even more, I'm interested in the dependency of this return probability as a function of n and of w when t goes large. So let's say t, let's say large, well, let's say t sufficiently large. I don't want to specify much. But here we are interested in the limit in which n goes to infinity. And essentially, we want to see if the system remains to a certain extent in the initial state, or it, let's say, thermalizes and goes everywhere. Go. Let's say a box distribution. Let's say a box distribution. So the distribution of the hi is just, let's say, box, so uniform between -w and w. Okay. Okay, good point. Yeah, please repeat the question such that. No, because since we'll be registered.
So I guess that this thermodynamic investigation is to see if your state can keep some information and build a memory, something like that.
Yes, okay. You can answer to this question in 2 ways. The first one is no, you want just to see if, let's say, thanks to this order, your system can break thermalization, and so keep there. And this is a question, if you want, okay, let's be more precise. If you really want to study the behavior n equal to infinity, I would say the answer that I gave now is the right one. If instead you have in mind a possible technological application, like, for example, I can build a memory out of this system of n spin, probably you are not really interested in the limit n to infinity, because it's already complicated to build 10 qubits. Imagine to go to a number of Avogadro. So, depending a little bit on your taste, yeah.
Thank you. Is your system independent of the topology?
I'm assuming, okay, here I'm assuming that this is just a line, a chain, yes. Of course, the answer is not, but let's assume the simplest case. Also because we don't have the answer for the simplest case, so. Okay, so let's see what we have been able to do during this, let's say, 20-ish years, using essentially the computational power. Okay, so this is the outcomes. So again, as I said, we want to see if in the thermodynamic limit, how this guy behaves as a function of W. Now, the very first result about this in the computational framework was probably around 2007 by David Hughes and Oganesian, in which essentially they came out with, again, I simplify a lot, but let's say they studied, because computational power, so what you can do is to fix a number of n and start to study the problem. So they could simulate n mean around, let's say, 8 up to n max around 16, let's say. Okay, so they simulated between 8 qubits and 16 qubits. They said they tried to extrapolate these results to the large n. And okay, here quotation are important, large n, let's say. And what they got is that PTW will be around 0, let's say around 0, if W is smaller than a certain critical disorder, which in these units is more or less of order 3. And instead will be non-zero, let's say different from 0, if W larger than WC. So this result, using the computational power, somehow told us that probably in the large n limit, we have a critical disorder. For disorders larger than this critical value, we will have, let's say, a memory storage, because, what I did, yeah. No, wait, I did the opposite, sorry. No, it's correct, it's correct. Large disorder, you have memory, yes. Because essentially, okay, you can see, because essentially this guy, if you do a Jordan-Wigner transformation, so if you go in fermions, let's say, this guy is a sort of traveling wave. It's just the Bloch theorem. So this guy tend to make you delocalize the states. So you put something and this spread. This guy is what preserves you to do that. Another more intuitive way, suppose that this guy become infinity. You don't have this term. This state will be an eigenstate of this term. And so the probability will be 1 forever. Okay, so this was the result. Now, let's again do our jump, and let's go to 2024. So we increased our computational power. What we have now, by many authors. Yeah.
So what you say is that particular state will be an eigenstate?
Yes.
But that's not what we mean by memory usually. If I choose any other state that I want to store, that will be lost to noise, right?
Exactly.
So there's only this one state that is stable.
No, but wait. This is an eigenstate if I go to the infinite disorder, strictly infinite, and I forget this.
Okay.
For finite disorder, this is absolutely not an eigenstate.
Okay.
So the main idea of MBL is exactly that if you want, contrary to integrable systems, your ability to preserve the information is robust against perturbation of the Hamiltonian. Cioè, people could ask, well, we know that integrable systems don't thermalize, so why don't you use an integrable system to store the memory? The point is that integrable systems are extremely fine-tuned. If you modify an epsilon of that system, thermalization immediately arrives. And so, if you want to try to sell to a company that you have a quantum memory and you ask infinite precision when you build it, probably the company will be not happy. Instead, here we are saying that this is a robust thing. It doesn't depend too much on the details of how the disorder is, so it's a robust phenomenon that is much more, let's say, applicable than just a fine-tuned situation. Provided you go above the threshold. And the idea is that the threshold is some value, some finite value, not infinite.
Sorry, about integrable systems, but maybe it's still undoable, and maybe I'm thinking too classically, but CAM theory would allow
CAM theory
you
is not applicable here.
It's not, okay.
If you want, CAM theory is not applicable anywhere, because you can check that what is the relevant thing? I think the distance from the integrable point goes to 0 extremely fast with the number of particles. So even classically, CAM theory, I'm not an expert. When I was in IBS in Korea, I used to be with experts on that, and they were saying that CAM theory is almost, we are recorded, right? So let's be a little bit less extreme, but let's say that CAM theory become almost irrelevant with systems with a realistic number of particles. But again, I'm repeating a slogan, so I don't take any responsibility for that.
So Dario, how about the coherence in this system?
I'm assuming there is no decoherence. This is a closed system, perfectly isolated, and yeah. Okay, let's go to 2024. So after almost 20 years, now we have n min equal to 8, n max equal to 26. So we have just been able to move from 16 to 26. Not exciting at all. And even more, now when we pretend to do this large n, the conclusion is that WC maybe does not exist. And if at all, WC is of order 30. So essentially, we end up with 20 years of development, 20 years of building up better and better computers and so on, in which essentially we agreed that the very first result was completely off, let's say by an order of magnitude, and maybe MBL doesn't exist at all. Definitely is not as exciting as the development in medicine. It's better that it is better the development in medicine rather than in MBL, for sure, for our lives, but still, we would like to do something better than that. So now, let's say the idea is to review why the problem is so complicated and why essentially the computational power didn't help us too much. Okay, I did a mistake. This part was better to keep. So let's erase this.
Leo,
yeah, please.
May I ask you the following? So, in principle, if this WC is a dimensionless number?
Good point. Technically speaking, here you have a coupling constant that determines let's say, the energy scale, and I decided to put it equal to 1.
Okay, my question basically is the following. If this number exists, it should be calculated from the theory. And the question is,
impossible.
What?
Impossible.
No, in principle, impossible.
In principle, yeah.
But in principle, I mean, in principle, this is possible. In practice, impossible. In principle, if this exists, this should be calculated. We should be able to calculate.
Yeah, let's say, yeah.
Okay. Yeah. And the question is, what are the parameters that you have in your theory that would give the same dimension of this WC? Because if you don't have enough parameters to build this dimension...
No, but wait, this is already dimensionless because I'm measuring anything in units of J that I fix to 1.
So this is dimensionless?
Yes.
So how many dimensionless parameters you have in your theory
If you want...
in order to scale this WC. But except n, which goes to infinity.
Yeah, the connectivity of the graph, I would say.
This is dimensionless?
Yeah, the number of neighbors that you have in your lattice, so in this case will be 1, and so on. This is definitely dimensionless. But this is a pure number, so...
But this is a pure number that has to be calculated from the parameters of your problem. It has to be there inside. Somewhere.
Well, I'm not sure I see properly the...
Suppose that I came out with a formula for this WC. I have to put there inside something that...
Okay, you have to put there, let's say, you have to put there J, that now I fixed to 1, but J is there. J is the coupling constant in front of there.
If this is 1, take it out.
Okay, then, as I said, you have the connectivity of the graph.
Okay.
Let's say that that is the most important thing. And then you should check, because, okay, let me give a very intuitive answer. I mean, not very intuitive. Yeah. The idea is that if you want, as I said, suppose that you go to the very infinite disorder, so this state will be an eigenstate. Now, when you turn on this state, you can think about doing first-order perturbation theory, and this state induces, let's say, couplings between the various states built in this way. So doing like first-order perturbation theory, you can start to, let's say, to count the number of resonances, so the number of hybridizations that you do between these states, and you ask if they diverge or if they stay few. If they stay few, PT will be 0. So, now I came. Another parameter that you have in your model is the mean level spacing. Like, how does it scale with n, and so that is another thing. Okay, so let's see why the problem is so complicated. Apparently more complicated than curing cancer. Let's see. Well, okay, to understand, let's see in principle. In principle, let's use the computational power. So what we can do is that we go at finite n, such that we have a certain H that now is a matrix. So you can diagonalize it and obtain EA, the energies, and the eigenstates. And then we can construct, let's say, P, T, W, N as a function of those. So let's say a certain F of, let's say, the various EA and the various A. And then we can scale N to be very large, N infinite. Okay, why this problem is so complicated? Well, the reason is because the many-body Hilbert space is a huge beast. And the reason is the following. As I said, this H is a function of the various, let's say, Pauli matrices. Now, let's see how these Pauli matrices are built. So we have a system of n qubits, and this is the Pauli matrix acting on the site I. So once you want to represent it, this sigma I A become the identity 2 by 2 in the first site of the spin chain. Tensor, the identity in the second site, and so on and so forth. We arrive at the I site, and we have sigma A, and then we go with the identities up to the N site. So overall, this guy is an object of dimension 2 to the N times 2 to the N. So we understand that we would like to study the problem N to infinity, but the actual parameter that is scaling when we do the computational approach is M, that it is of order 2 to the N, that is going to infinity. So that makes essentially impossible to use the computational power, because increasing by one particle means doubling the amount of stuff, let's say the dimension of the operators that you want to store. And this is an extremely bad scaling for the computational approach. So this is the reason why, if you want, passing from 16 to 26 is already a huge increase. But then we want to study something in the thermodynamic limit, and so we cannot go much. So let's say that this gives the idea why this is a very complicated task. Now, what we can do, so, okay, so let's say this shows that the scaling is very bad. And essentially, brute force computation cannot provide big, let's say, big achievement in this direction. So what we can do, and this is, if you want, my wishful thinking. Now I'm going to the part of the talk in which I hope something that we can do in the future, because so far we didn't do so much. Okay, the first is the very pessimistic approach, give up. In principle, we could say, okay, there is nothing we can do. The only solution will be to find a solvable model. Very complicated, but in principle, you could say, let's try to find another Hamiltonian with the same physics, but that allows some analytical treatment, and solve it, like the easy model or other models that have been solved in the past. The second approach, on which I work it a bit, is going to quantum computing. In principle, this is an idea that goes back to Feynman. In principle, if you want to simulate nature that is quantum, better to use a quantum computer. So quantum computing could be the solution. I work a bit on that, and there are very nice indications about that, but we know that technologically it's a mess. So I don't know. I don't want to be too pessimistic, but at the same time, I don't want to be like Minsky, like hope for something and then die before it happens. So I prefer don't give any prediction, or at least not 3-8 years. Otherwise, it means that I have to die soon. So let me avoid to commit about when quantum computing will be effective. I prefer to don't say a word. Then there is a third approach. And notice, quantum computing, in principle, already showed, if you want, we can, I think we don't have time to chat about that, but I'm open to discuss. We already have insights that quantum computing, when will be available, will be the solution. Let's say yes. Maybe there is an if. If will be, okay, I rephrase. Ricardo was asking if it is when or if. Probably if.
If you cannot solve that kind of problem with quantum computing, you're saying it won't solve anything, right? Because that is basically a qubit chain, right?
Okay, maybe I'm being too optimistic. Let's say that with quantum computing, I think, let's say that with quantum computing, when and if quantum computing will work, we will be able to scale to large number of qubits, and so hopefully we will be able to do a serious numerics. So start to think really about the large N, and then we will see the data and we will decide if we can do a large N extrapolation or not. For sure, with classical computing, we cannot hope to do a large N extrapolation with the 16 particles and hope to say something about the Avogadro number.
But there are quantum computers now that with few qubits. So, but you can try and see if.
Okay. This is going. This is a little bit too technical, probably. The point is that quantum computers, as far as I see, right now they can build decent number of qubits, definitely larger than those, but the number of reliable operations that you can do on those is fairly limited.
But that's because of the coherence and stuff
Yeah,
like that.
because of the coherencies and so on. So as far as I see, so far, quantum computers are even less powerful than classical. So I think if you publish a study with 26 qubits on a quantum computer, you go to Nature right now. And you can do it in a classical computer. So right now is not the solution. Let's see the third one. So the third one is still computational. But smart. And let's see what I mean by being computational and smart. But smart doesn't sound well. So the approach, let's say, why there is a room. Okay, so what I want to deliver now, if you want for the last part, is why there is potentially a room for being computational and smart. Let me remove but is horrible, come on. And. Okay, so let's go back to our Hamiltonian. So we had our Hamiltonian H that was defined in terms of n variables. And this guy gave us a 2 to the n Hilbert space. So we see that we have, and let's say our eigenstates are as well, so suppose that you build a certain, with the notation of before, a certain A, an eigenstate. This guy is still, let's say, a 2 to the n d vector. However, intrinsically, our Hamiltonian is defined in terms of n parameters. So, strictly speaking, if we were incredibly smart, these two n components are actually determined by just n parameters. So, if we were much smarter than what we are, we should be able to see the huge correlations sitting here. So, if you want, the message that I want to deliver is that this horrible scaling is not an intrinsic horrible scaling due to the physics. If you want, this is somehow the difference with the single particle problems like the Anderson model. In the Anderson model, you have a system of dimension n, so in that case, the scaling is better, but you have a system with dimension n and with n variables to store. In this case, and so there is nothing that you can do. You have to store the 10 variables, so there is nothing that you can do apart from going to analytics, so to system 1. Here, instead, in principle, there is a room because we have 2 n variables, but they are spurious. They are intrinsically defined in terms of just n variables. So the question is, can we discover these correlations? If the answer is well, yeah, please.
I'm a bit confused with the relation you're making there, because one thing is to say that the Hamiltonian for the system has a number of parameters.
Yeah.
And the other thing is how many parameters you need to specify a state, right? So think in terms of a free particle, right? The only parameter in the Lagrangian is the mass.
Yeah.
But if you want to specify a state for a free particle, you need 3 momenta, right? So the number of parameters to specify a state is not that one-to-one in relation to the parameters in the Hamiltonian for quantum systems in general, right? Or am I...
Yeah.
Exactly, that's
so
what I'm saying.
I'm saying that in principle you can, let's say, you have all the information to solve your system by just storing in your memory n variables. And then you can, for each state, you can in principle build that state.
Yeah, but that does not specify state, right? For the same Hamiltonian, you have a bunch of different
but
states,
in principle
and to differentiate them, you need more variables than parameters in the
but
Lagrange.
okay. So let's be more specific. I mean, here the idea will be to get just, for example, 1. So the idea, important. In order to discuss about, let's say, to discover the fate of MBL and so on, you don't need all the eigenstates. I mean, what I presented there needs all the eigenstates, but definitely that is an overkill. In principle, with a single or few eigenstates, so you could be able to. So, for example, you could say, no, I want to find just, let's say, few, let's say 10 or order of 10 eigenstates with the given energy. So you could start to think, well, I develop some algorithm that takes the n parameters and spit out 10 eigenstates. And this is a huge improvement, for sure. So, yeah, okay.
So,
just a small question. When you say computational in number 3, you mean classical computation?
Yes.
Okay.
So two things, yeah. So I kind of agree with this comment, but still I also agree with the linear n, because what you need in this is, what you really need is the number of quantum degrees of freedom. So how many quantities you can measure at the same time. For instance, if you have n spins, you will have the Casimir or the JZ for every side. Imagine
in any case, you will not have
so it's
an
not 2
exponential
to the
scale.
n, but it is n.
Yeah.
Right, so it's already much better. And the second thing what you're pointing out to there is somehow a dimensional reduction problem on a large data set, something like that.
Something like that. I'm saying that, yes, there are just, let's say, n parents parameters, and all the others are, let's say, determines as maybe complicated functions. But let's see an example that already worked it out.
Yes. On the same point, but I mean, this dichotomy between linear and exponential, I mean, you have in classical physics as well. I mean, you have a particle, the Lagrange might have even 1 or 0 parameter. The Lagrange might have 1 or 0 parameter, but then you have the initial condition, no? You have differential equation and the initial condition. The initial condition scales exponentially with the number of particles, whereas the parameter can be
scales exponentially with the number of particles, fine, yes.
So, I mean, this is not something quantum, and this happens all the time in differential equations too.
Okay, fine, yeah.
So, but then it's true that, I mean, if you want to map solution into states, that yes, you have exponentially growing number of states.
Again,
you find
I think
a way
here
to classify.
Here the real crux is that, let's say, the initial condition, okay, I didn't think carefully about that, but I think here the real crux is that you don't care too much about initial condition exactly because you want to find something that is generic, so it's not your core. And as I said, the idea is that you want to just to collect, for a given realization, so for a given thing, you just want to collect few eigenstates and do the statistics over there. And that is enough to solve your problem, that is understanding if you are localized or not. Let's see an example, because I think we'll clarify. So an example that already worked it out, which is the following. So, okay, we don't have much time, so let's say, brief. And it is essentially an application of this point of view. Which is the well-known MPS, matrix products state approach. So the MPS approach is an approach that is based on the idea that in many-body physics, in other problems, not in MBL, so this approach doesn't work in MBL, but in other problems, the states that you want to characterize are area, low, entangled. What do we mean by that is that suppose that this is, if you want your full state, you take a bipartition, so you take, let's say, you say this is state B and this is state A in the full space. Now, the entanglement, when you trace out the degrees of freedom and you compute the entanglement entropy of A, which is the same of computing the degrees of entanglement between A and B before the bipartition, the entanglement entropy is scaling like the area of A. This is what I mean by area law, to be, let's say, contrasted with the more general situation, which is volume law. So volume law means that when you compute the entanglement between these two guys, the entanglement entropy will scale like the volume of A. So will scale much more severely, if you want. And this is telling us that in the area law case, so this case, you have essentially only local correlations. So let's say a spin here will communicate and will, let's say, will have a correlation with the spin here, but will not have a direct correlation with the spin far away. When you are volume law, it means that everybody is correlated with everybody. Now, unfortunately, in MBL, this is not enough. You need also this part. But people in MPS realize that for many other problems, you could, let's say, live by describing only area law state. So in that way, you can say that people in MPS realized, yeah.
In that case that you showed the spin chain, you have local interactions, right?
Yeah.
So how can you have a volume life if everything is local? And you are
in
not
the thermalized in the thermalized phase, you don't. You have a volume law.
Yeah, but you are talking that in the MBL phase you will have like a volume law, or
no? In the localized case, you will have area law, but to describe the departure of okay, this is a good point. Cioè, there were let me.
Sorry, what's the good point?
The good point that he's raising, because he's saying, well, you want to describe the localized phase, so the phase in which your states are localized. So if you want for disorder large. So for disorder large, the entanglement will be area law. So he's saying, why don't you use MPS to describe the many-body localization? The point is that you don't want to describe the extremely high disorder case. You want to describe close to W critical. And close to W critical, you start to develop, let's say, entanglement that is not area law anymore, and so MPS doesn't work. Actually, in the past, people tried to say, okay, let's start with very large disorder, where MPS works perfectly. Then let's start to reduce the disorder, and let's see when the MPS approach break up. That is
But that is like a feature of whatever phase transition that you are in the, like nearing the critical point, you will have large correlations, right? So
yeah,
that means that I will get volume laws for every phase.
I would say most of the cases, yes. When the state is critical, MPS is not probably the best.
Okay.
It's not probably very nice. Indeed, people use MPS to study, let's say, the ground state of gapped systems because they are well described by an area law. Yeah, MPS is not going to work for this problem, but just to describe, let's say, the idea. So the idea is that if you want, people recognize that when you want to describe states that are area law, the situation is a little bit like the following. You have a huge Hilbert space that is 2 to the n dimensional, but the actual space of states that you want to describe is a very, let's say, this is the volume law case, and this is the area law case, and you want to describe just a very tiny portion of the Hilbert space. So can we find a parameterization that directly address these states without wasting our resources in describing states that we don't care about? So what they did in MPS was exactly to do that. And essentially, okay, let's be, let's say, fast. The idea is that your state, psi, of course, in general, can be written as, let's say, coefficients I1, IN, states I1, IN. So for each state, like let's say plus, minus, plus, minus, plus, minus, you have a corresponding coefficient. And this is, so if you want this guy, define for you an n indices tensor, which, as I said, is 2 to the n dimensional, very badly. However, people in MPS realized that in order to describe an area law entanglement, this is definitely an overkill, and they replaced CI1IN, which is a 2n, an n-index tensor, with 2n d times d matrices. So the idea is that your generic component, CI1IN, can be built as a matrix product like MI1, alpha, beta, MI2, beta, gamma, and so forth and so forth. So you make an assumption, an ansatz, you assume that your n-index tensor is much less general than what could be, and you assume that can be effectively described by 2n matrices, Mi, each of them lives in an internal space of dimension d times d. And then you can try to see if, with this ansatz, you can reproduce the states with an area law entanglement that you're looking for. And people saw that this can be done, and it worked. And essentially, you reduce the computational cost from 2 to the n to 2n d squared, and luckily, d doesn't scale, the dimension d doesn't scale badly with n, scale at most polynomial in n. So you reduce the computational cost from exponential in n to polynomial in n, which is much better. And this is why people in, let's say, area law business got success. Now, the hope in MBL, that at least I have, is that if you want, in this case, what we did was exactly, in a sense, what chemotherapy was doing for cancer. We recognized just the simplest pattern of the special states, being area law, and we targeted something to target them. In more general situation, there will be, again, patterns, because there are correlations. We have 2n components with just n parameters that describe them. So the idea is that there are secret, hidden correlations that are much more complicated to see, but they are there. And in the last 20 years, what we learned from AI is that neural networks are an excellent hunters for correlations. They can recognize a dog and a cat based on correlations between different images and so on. So they are really correlations hunters. So the idea that people are starting to develop under the name neural quantum states, that I think is very promising, is to train a neural network in order to recognize the correlations that we cannot see and reduce the computational scaling dramatically based on that. There are indications that this can work, but is still under debate. So this is the hope. Even more, even being like Minsky about AI, there might be a moment in which we will not use the neural network to discover the correlation and tell us if MBL exists or not. We could be able at a certain moment, maybe, to, let's say, ask the neural network, what kind of correlations have you learned? And this will be a key in order to understand better the physics, not just the final answer. So maybe there will be a moment in which we will use our neural networks to tell us what they have been able to learn about these patterns. But I think it's a long story, and it will take a lot of time. Yeah, thanks.
Questions about cancer and everything else?
No, cancer, please, no.
Very interesting talk, thank you. I have a question.
Yeah.
I don't know anything about this. These correlations that you calculate here, I mean, you know how to calculate the correlations, or you have to assume that a neural network yeah, a neural network is going to discover?
Right now, I cannot. I don't know. I think if you know how to calculate, that will be already an achievement, because you could start from finite 10 that you can manage and try to see which correlations are there. I don't think it's super well known, to be honest. I mean, you know that they are there because if you want.
What I'm thinking is, again, I'm dreaming. So what I'm thinking is, if you could, let's say, imagine which are the correlations, and you could
repeat.
If you could imagine which is the type of correlation, and you could calculate something like that, I mean, you could do some of those things that are called recurrence maps or something like that, in order, and then follow them in time in order to know, I mean, which would be the ones that persist, let's say.
I don't have an answer. I don't know. The only example is super simple, as I said. Here, if you want people recognize, well, super simple. It was already super smart, but let's say a posteriori is very simple. You recognize that in order to describe a system that has an area law entanglement, you don't need an n-index tensor. Two n matrices are enough. And out of that, you say, okay, let's parameterize our n-index tensor out of these matrices, and then let's try to optimize via a cost function these matrices in order to well approximate the state that you're looking for. In principle, I guess that if you have a good understanding of what correlations are there, you will be very close to find a solution to the problem. So I would say probably not, but yeah. That is a sort of, I would say, what you are proposing is a sort of combining point 1 and point 3. Point 1 and point 3, in a sense, almost giving up and go to analytics, but at the same time, keep in mind that you don't want to solve the full system, but just discover where the correlations are and then hunt them with the computational team. Maybe it's very smart. Yeah.
So Dario, we have a bunch of students here. Some of them are master students. So my question for you is, what kind of problems they could expect you to supervise them if they look for you for PhD in many body systems and quantum information?
Also the quantum computing part. There are. I mean, I didn't discuss about the quantum computing part. So the point 2, if you want. So how you can try to use quantum computers in order to address this point, or how you can hope that future quantum computers will address this point. This, as I have to admit, I never work in neural quantum states, so I cannot declare myself an expert on that, but I believe it's extremely promising. It's probably the only promising approach right now, apart from analytics. And definitely is a new, I would say the idea of neural quantum states is from 2019, I think. So it's fairly new, it's 5 years old. So there are also, I think, simple enough problems that can be addressed. Yeah, it's a message for you guys.
If students want more details, that's an opportunity, or later at the coffee break. Any other questions? Yeah.
Yeah, so at the end in the disorder problem, you have your Hamiltonian and you are tweaking you're changing the parameters, right? But what MPS does is that they serve because you have, they are useful because you have this kind of very special structure of entanglement.
Yeah.
But if you change the disorder, you are changing the entanglement structure. So
no, wait. You say if you change
because for MBL,
the disorder realization or the disorder strength?
No, the disorder realization.
Right, but the beauty is that if you find a general enough pattern like being area law, it will be disorder independent. Cioè, suppose that you have a disorder strength for which you are area law. Then the MPS ansatz will work. You just have to re-optimize. But this is...
my question is so physically, the entanglement structure of many-body systems is really, really complicated.
No, I'm not saying that is an easy problem.
So, yeah, but suppose that you somehow make an ansatz for a network. That
okay, I see what you mean.
If you change the
I see what you mean.
You are changing.
I think what you are talking about is very close to the usual problem of overfitting.
Okay.
Cioè, okay, let's... how much can I talk? Okay. So, I think what you're saying, let's say, in abstract... so I can do whatever I want. Okay, stay sit. Okay, so what is? So I think what you are talking about is exactly this. So suppose that you have a certain set of experimental, let's say, numerical data that goes, let's say, they want to reproduce, let's say, a curve like this, but then you have noise. So, and okay, let's say that this is what you want, somehow disorder averaged, and this is what you get. Now, this is the standard situation in neural network, right? In machine learning, people fight with this forever. Because essentially, if you have too many parameters, you start to fit. I mean, instead of recognizing the global pattern, you start to fit the fine details. And so your model will not work well when you change the disorder.
So you think that this kind of like neural network ansatz will be like useful in this case because they are already built in the base that they don't care pretty much about
I think that the fact that people in deep learning has been able to overcome a very similar problem, I think gives hopes. And okay, now let me, again, I'm not pretending to be an expert on that, but let me just, let's say a funny story about what happened in deep learning. So as far as I know, in deep learning, the following thing happened. People were well aware of this. Is it clear, the problem that William is mentioning? So the idea is that if you have points that are, let's say, distributed according to a certain law that you want to learn, but then there is noise, and so you have fluctuations around. Now, the idea is that if you have a neural network, let's say a machine learning algorithm with too few parameters, you will be not able to, so again, let's repeat. So we have this plus noise. Now, the idea is that if you have, and you want to reproduce the real behavior and not the noise. So the idea is that if your neural network has too few parameters, probably we'll try to approximate this curve by something like that. Horrible. Then you start to add parameters, and so you're, let's say, you start to get the capacity to follow the trend and get in this. But if you add too many parameters, then you start to see all the noise, and you start to fit all the noise. And this is what people call overfitting. So they were using this kind of plot in which here you put, roughly speaking, the number of parameters, and here you put, let's say, the error. And they were saying that, let's say, this is the, let's say, the test error. So if you want the error that you do after having trained the neural network when you go to new data and you try to fit the new data. And here is the training error. So this is a decreasing function that becomes better and better. And they were saying, okay, so there is what they call the sweet spot, which is the point at which you have a fairly good agreement with the training data, but not too good, but also not, let's say, you are in the best possible scenario, because then when you start to increase the number of parameters, you start to fit the noise and you are screwed. Now, I don't know the details, but the revolution of deep learning has been to realize that if you go to the over-parameterized regime, which is the phase in which you have so many parameters, much more than what you actually need to fit the train and the noise, the curve goes back again to 0. So this is, I think, something that could help in this case as well. I think that exactly the same. Now, this is very surprising a priori, that overparameterization can be good. But then I realized that our brain has so many parameters, and we can recognize patterns without overfitting. So I believe that it's not something so crazy a posteriori. But I don't pretend to understand it, and I'm not sure it's understood.
But we know this in physics for long. If you make a lot of mistakes, enough mistakes, then eventually you do the right thing.
Ah, yeah, good. Yeah, agreed. Yeah.
Other questions? So thank you very much for your very comprehensive